Day 8 in Switzerland, Geneva. Arriving Geneva from Bern. Hotel Ibis, Geneva, Aeroport. Room tour. Taking bus at Geneva Airport Terminal. Change to a tram for CERN. Geneva is the second most populous city in Switzerland, about 204,000. It is a French-speaking community. It is an international financial center and worldwide center for diplomacy. It hosts many international organizations like United Nations, Red Cross, WHO, CERN, and etc. Arriving CERN. The sculpture of wondering the immeasurable. Register for admission. A Lego model of CERN. Component of the Large Hadron Collider, LHC. CERN stands for European Organization for Nuclear Research. Particles are accelerated to speed of light and collide. Detectors observe and record the result of the collisions. The analysis provides insights into the fundamental law of nature.
Conditions at the LHC reproduce the conditions that existed a trillionth of a second after the Big Bang in the first instance of the universe. How do we detect these new particles? By measuring their path and energy with special detectors built in layers around the collision point. The LHC detectors are extremely fast three-dimensional cameras with almost 100 million sensors taking up to 40 million snapshots per second with incredible precision. In over 60 years of existence, CERN has played a vital role in understanding the innermost structure of matter thanks to its research with particle accelerators and detectors, which have provided the overall framework to explain the basic constituents of matter and the forces that act upon them. This framework is known as the Standard Model of Particle Physics.
The Standard Model of Particle Physics describes all known particles and their interactions. Admittedly, it has a rather boring name. It should be called something like the Amazing Theory, because it is the most accurate scientific description of reality to date.
The discovery of the Higgs boson, the final piece in the puzzle of the Standard Model, announced at CERN on the 4th of July 2012, was a triumph for particle physicists at the Large Hadron Collider.
Rich energy. And the stuff that we're made of is only a few percent of the total energy of the universe. Dark matter is about a quarter, 25%. Dark energy accounts for the rest, so about 70%. But dark energy is something that we haven't been able to come up with a way to study at CERN. So we can go and study the next largest chunk of the universe, dark matter.
I think the greatest discovery that we could make would be something completely unexpected, something that no theorist has written down yet.
The LHC is now running at almost twice the collision energy and with higher intensity than in 2012. Scientists hope that the LHC experiments will help to further explore these and many other questions in our understanding of the universe at its most fundamental level. In its unending quest for knowledge, CERN has pushed back the frontiers of technology by developing new tools for its research. Much of this innovation has taken place in-house, with many new technologies finding applications in our daily lives.
As you might remember from the beginning, CERN is the birthplace of the World Wide Web and developed an early type of touchscreen way back in the 70s.
The colossal amount of data generated by experiments at CERN and the unprecedented need for storing and distributing them to the world for analysis have pushed computing technologies to their limit. Today, about 500,000 processor cores are required to analyze the data produced by the LHC collisions. This requires the interconnection of more than 170 data centers around the world in what we call the worldwide LHC computing grid.
But let's be clear, our core business is fundamental research of particle physics. By pushing the frontiers of knowledge further every day, physicists push technologies to their limits, and even invent new ones to make their experiments work. In this way, CERN has contributed to many technological innovations, from the web to grid computing to more accurate methods for diagnosing and curing diseases like cancer, and much more.
What is dark matter made of? Is dark energy real?
This is science in progress. And to solve the mystery, we need more data.
Particle accelerators have been unveiling the structure of matter since the discovery of the atomic nucleus more than a century ago in 1911.
The general trend has been to build larger and larger particle accelerators because the scale of detail of fine grain that you can detect gets smaller and smaller as the energy of the accelerator gets bigger and bigger. So when you want to know more and more about what's really inside of these elementary building blocks of every substance, you are obliged to build bigger and bigger accelerators.
Accelerating particle beams is an exclusive technique to probe the structure of matter and understand the underlying laws of physics. In addition, the high energy densities achieved in particle accelerators approach those present in the primordial universe, fractions of a second after the Big Bang.
The best tool that we have is particle accelerators. The unique feature of particle accelerators being able to give you all the parameters of particles that we want. It is the primary tool that we have. So is there a good reason to go to higher energy or different kind of accelerators.
New physics can be accessed by increasing beam energy and by increasing the rate of collisions to maximize the probability that the particles of the counter-rotating beams interact. Currently, CERN is upgrading its flagship accelerator, the LHC, to know more about this very special particle. With the high-luminosity LHC, the potential for new discoveries will be expanded by a factor 10, allowing physicists to study known mechanisms in greater detail and observe rare new phenomena. The quest for higher energy requires larger and larger accelerators, with implications for the cost, energy consumption, and complexity. Currently, R&D efforts aim to reducing size, cost, and environmental impact through innovative technologies. Larger and higher energy accelerators would be useless without bigger, faster, and more sensitive detectors to capture rare phenomena and minute details. These discovery machines pose significant challenges for operation, distributed controls, maintenance, and installation. Revolutionary computing infrastructures, powered by AI and novel technologies, will be essential for processing and analyzing the even vaster amounts of data generated by the new machines, pushing the limits of technology and innovation in many different domains. Since the creation of CERN in 1954, the unprecedented scale and technical requirements of the accelerators, detectors, and computing infrastructure needed by particle physicists has constantly pushed to the boundaries. Einstein's theory of relativity brought about the notion of space-time, with the speed of light as an absolute speed limit and time that flows differently for observers moving in different ways. Einstein's general theory of relativity expresses gravity as deformations in space-time, explaining how the universe functions at large scales. In parallel, quantum mechanics changed our perception of the world at the microscopic scale, from a strict and precise clockwork-like system to a strange place governed by probability and uncertainty. The study of the laws of nature continued in parallel at the two extremes. The theory of relativity led to a number of spectacular predictions like black holes and gravitational waves that have now been observed in nature. Decades of studies of particles and their interactions led to the establishing of the standard model of particle physics that unifies two of the four known interactions, the electromagnetic and the weak force, into a single electroweak theory, and describes the third interaction, the strong interaction, in the same language. But even electromagnetism still holds some mysteries, like the hypothetical existence of fundamental magnetic monopoles, particles that are just a single north or south magnetic pole. Quark-gluon plasma is a state of matter governed by the strong interaction, where quarks and gluons are not confined within hadrons. It's crucial for understanding the early universe, moments after the Big Bang, and can now be reproduced and studied in particle accelerators. The fourth interaction, gravity, is not included in the standard model at all. Developing a theory of quantum gravity that successfully unifies quantum mechanics with general relativity remains an outstanding challenge. In addition, there are a number of features in the standard model that arise without an explanation. The fundamental building blocks of matter are 6 quarks and 6 leptons, arranged in 3 families, but we don't know why there are exactly 3 of these families. We understand the mechanism that gives these particles their masses since the discovery of the Higgs boson in 2012 and the studies of its properties that followed, but the mechanism does not predict the values of these masses. We can measure them, but we cannot explain where they come from. The lightest of the matter particles are the elusive neutrinos. We know their masses are not zero, thanks to the discovery of neutrino oscillations. But those masses are so small, we haven't been able to measure them directly. And they cannot be explained by the Higgs mechanism without adding extra particles or mechanisms to the standard model. The Higgs mechanism itself leaves many questions open. Puzzles such as the shape of the Higgs potential and its implication for the stability of the universe and the unnaturally low mass of the Higgs boson inspire new theories beyond the Standard Model and extensive experimental studies of the Higgs particle. All matter particles have mirror images in the form of particles of antimatter. Matter and antimatter should have been produced in equal amounts in the Big Bang, but if this was the case, today our universe should be empty, since matter and antimatter annihilate when they meet. Instead, the universe appears to contain mostly matter. Some unknown mechanism tipped the balance and more matter than antimatter was produced. That little excess is all the stars, galaxies, everything we see around us. In addition, those stars and galaxies and all matter that we know only account for a tiny fraction of the energy and mass in the universe. From the way galaxies rotate, we know that they must contain a new kind of matter that we call dark matter. We observe how dark matter bends and lenses light traveling between galaxies, but this matter is not made from quarks or leptons. While dark matter could account for the extra mass we observe in galaxies, the accelerated expansion of the universe needs some new mechanism to be explained. Referred to as dark energy, it is thought to make up about 70% of the universe's total energy. Its nature is one of the greatest mysteries in physics. What is the next step? Do all particles have some inner structure that we haven't yet observed? In string theory, they can be described by tiny strings vibrating in different ways. String theory also predicts the existence of additional spatial dimensions beyond the familiar three, but each way in which these dimensions could be shaped gives rise to a potential universe. So is the one we live in just a special case of a vast landscape of possibilities? With new clues from experiments and further developments in theories, the quest to make our universe a bit less mysterious continues.
This is the world's first web server. The compact muon solenoid detector. The particle accelerator in the tunnel. by antimatter truck. There are installation Chroma 7 by Yun-Chul Kim. Round about 4 dimensions by Julius von Bismarck. Cover Tina Unfollowed Alice by Chloe Delarue. This is the quantum world. Quantum World explore how the universe works at tiny scales. Souvenirs. Arriving downtown Geneva. waterjet shadow de Geneve. Lakefront Geneva. Pont du Mont-Blanc Bridge. Jardin entrance, English Garden. Fontaine de Quatre-Saisons, Fontaine of Four Seasons. Sculpture Abrimaux. The flower crop with no flower. Boat cruise across the lake. Arriving the other side of the lake. World Meteorological Organization. United Nations. United Nations. United Nations headquartered in Europe. The broken chair serves to remember the victims of bombs and landmines. Riding on a train, return to hotel. Swiss Chalet restaurant at Geneva Airport. Lamb meatballs with macaroni. Chicken with smashed potato and vegetable. Leaving Switzerland from Geneva Airport the next morning. Goodbye, Switzerland. Please like, subscribe and share my videos and my channel. Arriving Toronto. Thanks for watching. Beautiful sunset while descending to Pearson Airport. See you next time.